Hi everyone, welcome back. It's been a while since I posted a video. I wasn't originally planning on posting the labs online because I didn't want to encourage people not showing up to class, but I think it's been a while since we looked at these labs and a lot of people may have forgotten some of the concepts. So I'm just going to go over Model 4-1. Now I do change the lab every year, and I actually have already made changes to the lab from this year, so I'm just going to do a slightly different version of what we covered in class, but all of the same concepts are going to be covered. So without further ado, here is the model 4-1. It's modified from the textbook, so if you want to follow along with the textbook, there are a few differences. So we have here an electronic assembly and test system of two types of electronic units. I'll just slowly scroll through so that if you want to pause this video, you can make note of any differences between this and the book. One difference is that I have included all of the travel times. So Model 4-1 in the book doesn't have any travel times between stations. I believe everything else is the same. I'm going to get started on building this model. I'm just going to move this out of the way so that we can see what we're doing in Arena. So we are told that there are two types of parts that arrive in the assembly area, Part A and Part B. So we can create two creates. And just for the sake of time, rather than opening up each of these dialog boxes, I'm actually going to do all of the editing down in the spreadsheet view. It just makes things go a little bit faster. So Part A arrives, Part B arrives. This entity is Part A, Part B. This is an exponential distribution with a mean of 5 minutes. This is an exponential distribution with a mean of 30 minutes. And Part B arrives in batches of 4. Upon arrival, Part A is transferred to the Part A prep area. So we can model a transfer. There are more sophisticated ways of modeling transfers and more with higher level logic. But if we just want to show that some time has to pass before it arrives at the next station, we can just use a delay module. So that's what I'm going to do here. I'm going to create a delay module, and I'm going to call this to a prep. This is a transfer, and the delay is uniform between 1 and 5 minutes. Upon arrival, Part B, the batches are separated and transferred to the Part B area, taking a minimum of 2 minutes, a mode of 3 minutes, and a maximum of 5 minutes. So we can add a delay here. Call this 2B prep. It's a transfer, triangular, 2, 3, 5. Okay. And then once Part A arrives at the Part A prep area, this is a process. This is a workstation with a single operator. So what we can do is, I will actually open this dialog box. We can call this Part A prep area. And the action here is a seize delay release. Usually when we are modeling basic workstations, there are resources at that workstation that are used when the process is running and are not used when the process is not running. And so that would be a seize delay release type logic. The other types of logic we may see in other situations. But since when we come to the prep area, the prep operator is going to be busy, and when we leave the prep area, the prep operator is not busy, we're going to call this a seize delay release. And we're going to add a resource, and this is going to be the Part A prep operator. The delay at this process is a triangular distribution in minutes. and it's a minimum of, where is it? 1 minute, a mode of 4 minutes, and a maximum of 8 minutes. Similarly, there's the Part B prep area, and I will just do this down here. Part B prep area. Seize, delay, release. We need to add a resource. This resource is going to be Part B prep op. And this is also a triangular distribution in minutes with a minimum of 3, a mode of 5, and a max of 10. Now we've created these resources. We can actually go to the resource tab and take a look. And these two resources that we defined in these processes are now here. And this happens automatically. Similarly, we created these entities. We named these entities in the arrival streams. So now if we go to this entity spreadsheet, we have these entities here. And this is where we can possibly change what these entities look like. So I can say Part A is a green dot and Part B is a red dot. And then when I'm watching the system in motion, I'll be able to differentiate between parts A and parts B. So coming back to our model, once parts A and B have been prepped, they're transferred to the sealer, taking 1 minute and 2 minutes respectively. So let's add these delays. Now, I was doing it automatically earlier, but what I was doing was I was clicking on the module that I want to link to, and then dragging over the new module. And what that does is Arena will automatically put this link in place. So this is A to sealer. This is a transfer, and this is a fixed value of 1 minute. In contrast, if I don't click this and I just drag my delay module out, it doesn't connect to anything. And so let's see, B to sealer, transfer 2 minutes. So I would need to go and connect this manually. And the way I do that is I can come up here to the connect tool. And if I click this, I can come and connect this exit node to this entry node. And it's connected up. So now I'm told that at the sealer, these units are assembled, tested, and sealed. And the process time, well, let's first go ahead and create our process. So we're going to have a process here. This is the sealer. It is a seize, delay, release. The resource is the sealer machine. But the delay type is different. We don't know what this delay type is. So we have different delay types depending on which of the entities, which part type it is. So what we can do here is before we get to the sealer, we can assign this delay distribution previously using the assign module. So we can create here an assign module for parts A and B. And we can call this assign A sealer time. And this is an attribute. This is an entity attribute. So every entity has its own attribute, and we're going to call this attribute sealer time. And in this assignment, we're going to say that sealer time is going to be pulled from a triangular distribution with 1, 3, 4 as its parameters. And so what will happen is anytime a part comes through, it will see that it needs to be assigned to this attribute called sealer time, and it will randomly pull a number between 1 and 4 with a mode of 3, and that will be according to a standard triangular distribution. So every entity will have a unique sealer time attached to it, and that sealer time will be saved and it'll carry it with it throughout the system. So we can say OK. We can do the same thing for part B. We can say assign B sealer time. add an assignment. Again, it's an attribute. I can retype sealer time, but if I look now at this down arrow, actually listed at the bottom, because this is an attribute that I have named elsewhere in my system, so it shows up as an attribute. So I can name sealer time, and this is a Weibull distribution with a beta parameter of 2.5 and an alpha parameter of 5.3. And now when I get to the sealer time, I don't want to pull from any distribution where I'm getting numbers. I want to reference the attribute that has been attached at these assign modules. And that attribute name was sealer time. We can type it in directly, but if you're afraid of making a mistake, you can right click and go to build expression. And it's an attribute. And the only attribute we have defined is sealer time. And so this way we're sure not to make any typos and mistakenly have references to things that don't exist. Once leaving the sealer area, 91% of the parts pass inspection, and the remaining 9% of the parts are sent to the rework area. So we need to do some sort of a branching logic. So we're going to use a decide module. And the question we're asking is, did the part pass inspection? We just have two ways it can go. It either passed or it failed, so two-way by chance, and 91% of them passed. So 91% will pass, 9% will fail. So 91% of the parts pass inspection and leave for shipping, taking 5 minutes. So let's add a delay and then a dispose. And this is, let's say, sealer to shipping. Transfer, it's 5 minutes. And this is shipping. The remaining 9% of the parts are sent to the rework area, taking 2 minutes. So we can put a delay. Let me click on this and put a delay. And it gets sent to the rework area, the rework process. This is a seize delay release. Oops. And we have these rework texts, and we have 2 of them. So it's very tempting to put the number 2 in this box. Let's see what it says here. This is the number of units to seize or release. So every entity that comes through, how many of these resources is it going to seize? So if we put 2 here, that's saying that for every 1 entity that needs to be processed, we need 2 rework technicians. And that's not true. We have 1 rework technician that can work on 1 entity, and then the second rework technician can work on a second entity. So we want to make sure that each entity is only seizing 1 rework tech. And then we want to define in our resources that the rework techs have a capacity of 2. So now this shows us that there are 2 rework techs that can work on 2 different entities at the same time. So in this rework area, we are told that this process is an exponential distribution. And let's change this allocation, non-value added. If you're not sure about these allocations, you can just ignore them. It's just another way to categorize the time that the parts spend in the system for analysis later. But since this is rework, and in a perfect world, it would not have to be done, right? We would do everything correctly the first time. We're not actually adding value by fixing our own mistakes. So this is an exponential distribution with a mean of 45 minutes. And then after leaving the rework area, 80% of these rework parts are salvaged. So we can put another branching logic. And we have 80% are salvageable and are sent to the shipping area, taking 2.5 minutes. And then the remaining 20% are discarded as scrap, and it takes 2 minutes to travel to the scrap yard. So we have a delay. Two minutes. And so we can create we can bring a dispose module out and call this scrap. And so the question is, now we know that these salvageable parts go to the shipping area. The question is it the same shipping area? Logically, physically, we would say yes. So we can connect this exit node to this shipping area, to this dispose. However, I personally like to have separate dispose modules just so that we can keep track of statistics of the streams that different entities are flowing through. So I'm going to create a separate dispose. This is also the shipping, a shipping dispose, because this is just a logical model. I'm going to call this reworked shipping. Okay, so now we have our model built. Let me zoom out a little bit. It looks pretty long. I'm going to see, maybe I can bring some of these guys down so I can fit them all on one. That's a little better. So now that we have our model built, we want to run the model and we want to check our performance measures. So we want to run our model for 4 consecutive 8-hour shifts. So that's a total of 32 hours. And we want to look at our final results in minutes. If a process takes 0.1 of an hour, I don't automatically think, oh, that's 6 minutes. So it's easier to see these in minutes. And then we're just going to do one replication so that we're not, just to make sure that everything's running. So let's hit OK. And I'm going to come here and call this model 4.1, apply, OK. And I'm actually going to save this on my desktop. So I'm just going to go to save. I'm just going to save it to my desktop. Okay, so now we're ready to run. Let me slow this down so that we can just watch it very slowly, and I'm going to hit play. So now we see my green dots are the part A's, my red dots are the part B's. And we're coming through and queues are forming up and things are waiting in line. And we can speed this up a little bit more. Actually, these dots are pretty small. I can make them a bit bigger, but it's okay for now. And so I'm just going to fast forward now till the end. So I'm going to hit the fast forward button. It's just going to fast forward, and it asks me if I want to see the results. Yes, let's look at the results. Okay. So the performance measures of interest are resource utilization, and I can see here that my resources are utilized according to this percentage. It looks like my rework texts are the least utilized, and my part B prep operators are pretty highly utilized. This is a very high utilization rate for a resource, over 90%. These guys are very busy. they might need a little help. So we are looking at the resource utilization. We can also look at the average number in queue. So this is the average number waiting. Again, we can see that Part B prep area has really long queues on average, and the amount of time in each of these queues, 178 minutes average, that's close to 3 hours, and the maximum value, doing math, that's almost 6 hours. That's a very long time to be waiting in line. So clearly Part B area is our bottleneck. And we also want to know the time and system for first time through parts, for salvaged parts, and for scrapped parts. If we come here to the entity section, and we can see that there are all these metrics for time, they're all divided up by part type. We have part A, part B, but we don't have anything that shows us how long it takes on average to go from either one of these to this exit point, from either one of these to this exit point, from either one of these to this exit point. So there's nothing here that tells us that. So we need to put in our own user-specified statistics. It's not in the default report that we get. So I'm going to stop running this model, and I'm going to make a few modifications. I am going to move all of these guys over so that I keep track of when each of these parts arrive. So I'm going to add an assignment now. I'm going to add an assign, and I'm going to call this assign A arrival. Again, this is an entity attribute, and I'm going to call this arrival time. And the value for this is going to be T now, which is the arena expression for current simulation time. If you didn't know this by off the top of your head, you can right-click and go to Build Expression. It's down under Date and Time Functions. And if you click on Current Simulation Time, the current expression will be T now. If we wanted to know the final simulation time, it's T fin. And then there are all these other different functions to know the times in the times and dates in the simulation. So we're going to do T now. Okay. And we're going to do a similar thing here for part B. Okay. And so now if you are following the book, you may notice that these sealer times are actually in the same assign module. And that is something that can be done. I can add a second assignment. I can add a bunch of things that I want to attach to the entity the minute it shows up. But it can also be done separately. So whether you put both of these these assignments along with this arrival time assignment, or you keep it separate, it doesn't matter for the logic. So now we have our arrival times defined, and we can go ahead and record. Let's do record, record, record. We can record the time interval between when arrival time was first stamped and when it comes to this point. And we're going to call this first time through time in system. And call this record first time through time in system. We can record reworked time in system. And we can record scrap. Okay, and so we can run this again. Just so I don't overwrite my old report, I'm actually going to come and name this project something different. So I'm going to call this V2. Okay, so I can do this again. I can hit play, and I can fast forward till the end. Look at the results. So if we look at the difference between these two reports, we can instantly see that the difference is now I have an extra section called user specified. So if we go look at that, we can now see that we have this tally. We have the time interval between the when each of the entities first arrive, the T now when they are created, and the time when they leave. And we can see here that on average, these are the number of minutes that the parts spend in the system, which, to be honest, these are all pretty high. I think probably that bottleneck at part B contributes a lot to this, but we can take a look when we do some analysis of the system. So we now have a model of our current system that we can experiment with. We can add resources, we can remove resources. We can say, what happens if we increase the number of people working at the Part B prep area? Let's take a look. Okay, let's run. Okay, these have dropped dramatically. Keep in mind that we only ran the simulation once. We only did one replicate, and so we should not be basing any decisions on the numbers that we just looked at. We should do multiple trials because a single replicate does not tell us good enough information that we can make decisions on it. So I hope you found this video helpful. I will be back with model 4-2.